In this lecture, we are going to see what is the number system and how we convert numbers among different number systems. Number system or system of numeration is any sort of counting system with some base value. If the base value is 2, we call binary system, and it uses two symbols, 0 and 1. And if the base is 3, we call ternary system, and if the base is 8, octal system, and uses numbers from 0 to 7. And if the base is 10, is our decimal system and uses symbols from 0 to 9. If the base is 16, we call hexadecimal system and uses numbers from 0 to 9. And 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. It uses 16 symbols. Here is some conversion examples which converts a binary numbers to other number systems. At first, we'll see the octal conversion. Here is the binary bit to stream. We cut 3 bits from the bottom to up. The first bit, 3 bit is 2, next is 2, next is 7, next is 0, next is 3, and last is 1. It just completed the octal conversion. To convert to hexadecimal value, we cut the bit stream by 4 bits, and this result 2, and this result D. D is 13, this result 1, this result B, and B is 11. There are 3 ways to convert to decimal. First is we use the result of hexadecimal value. The order position is here is 0, 1, 2, 3. So if we use hexa result to convert to decimal, here is B 11 and order 3, 1, order 2, 13, order 1, etc. So the result is this value. And if we use octal to decimal conversion, here is the octal conversion. The coefficient 1, 3, and the exponent 5, 4, 2, 0, and we get the same result. If we convert from binary to decimal directly, here is the equation, and the coefficient is 1, and the order position from bottom to here is 15 position. So the exponent is 15, 14, 13, 2, 0, and we get the same result here. This slide shows some examples which convert a decimal number to binary. Here is decimal number, and we convert from decimal to binary first. We break down this number by the 2's powered number. This. If the powered number exists, we simply put 1 here. That's because this position is here. If this position is here, we just put 1 here. But we cannot find this power of 2. There is no power of 2 terms in equation, so we put 0 here. By doing so, after decomposing the number 2, the power of 2, we simply put 0 or 1, whether it exists or not. That's very simple. From this binary bit stream, we can convert to octal, and we can convert to hexadecimal very easily. Next, let us see how an integer is treated inside of a computer. The number of bits determines the maximum integer. Overflow error occurs when bit lacks. Can expand bit length to 64 or 128, but limit exists. Here is some example of integer range. When we use 16-bit, the range is like this. That's because MSB, most significant bit, is used as a sign bit. If we use 32-bit, the range is like this. Let us see how a real number is treated inside of a computer. The real number is expressed as Mantissa and exponent. Here is an example. Is Mantissa and exponent, and the base is 10. The Mantissa and exponent. But in binary system, base cannot be 10, so the binary base should be used. If the base is 2, it seems like this. If the base is 8, it looks like this. If the base is 16, it looks like this. You may catch that there can be some precision problem in representing a real number as internal format of a computer. There cannot be infinite lengths of bits for number conversion, and there can be a truncation error. In this last slide, we'll see the basic operations of the Boolean algebra. The Boolean algebra was invented by George Boole, and it defines the logical relationships between two numbers, 0 and 1. Here we have two numbers x, y as input, and there are 5 operations, and the first operation is AND, and it is the result of multiplication of two numbers. If you multiply two numbers, we get this result. And OR operation is something like the summation of two numbers. If the summation is greater than 0, we get 1. If the result is 0, the result is 0. Exclusive OR is If the two numbers are same, the result is 0. And if the two number is not same, the result is 1. NAND is the inverse of AND. We represent the head bar of AND, and 3 zeros are inverted to 3 ones, and 1 is inverted to 0. NOR is the inverse of OR, and we represent like this. 0 is inverted to 1, and 3 ones are inverted to 3 zeros here. In this lecture, we have learned what is the number system and how to convert a number to another number system. And we also learned how a number is represented inside of a computer and learned the basic operations of a Boolean algebra.